Okay, in this video we're going to be looking at trends in ionization energy across a period and down a group. So first of all, we'll be able to define first ionization energy. It does come up in the exam, the definition, so we need to be able to memorize the definition, also be able to write an equation for first ionization energy and perhaps even second ionization energy. So we'll do that. Secondly, we need to be able to state and then explain the trend across a period, and then state and explain the trend down a group. Let's start off with the definition for first ionization energy. Here we are. The energy required to remove 1 mole of electrons from 1 mole of atoms to form 1 mole of ions, all in the gas phase. And in the exam they may ask you to write the equation, so let's do that. The equation, right. We'll use any element. They may ask you to write the first ionization energy of sodium or for chlorine or any other element, but let's just generalize and call our element E. We're removing an electron and we're going to make a positive ion, and there is our electron that we have removed. There it is. And don't forget to put gas. Oops. Gas there and gas there. That will be the first ionization energy equation. They may ask you to write the second ionization energy equation, and if they do that, then you start off with E plus. That goes to E2 plus, and there's electron there that's been removed. Put gas and gas. Remember that you must start off with 1 plus to make the 2 plus. That will be the second ionization energy. Alright. Okay. Let's now look at the trend then going across the period. Here are the elements, the atoms for period 3. I've just drawn them as circles: sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine and argon. Notice I've drawn them getting smaller, so the radius is getting smaller going across the period. And the reason for that is nuclear charge is increasing. Right, that is increasing, and you know the reason why. Atomic number of sodium 11 protons, atomic number of magnesium 12 protons, aluminium 13 protons. So the nuclear charge, the positiveness of the nucleus is increasing, which means that the outer shells are being pulled in. So therefore the atoms are getting smaller. Shielding effect is constant, as you know, because the number of shells stays the same. They're all in period 3, so they have 3 shells each. So the outer electron is not being shielded anymore as you go across the period. The shielding effect's the same. Right, so that effect therefore is the atomic radius decreases. If that's the case, the outer electron, can you see, is going to get closer and closer and closer to the nucleus, which means that it's more tightly held, more difficult to remove. Therefore the ionization energy will increase going across the period. So the trend, stating the trend going across the period, ionization energy increases. Right, let's see if we can draw a sketch of the first ionization energy against the ionization energy for each of the elements, sodium to argon. Right, I've drawn it as log ionization energy just to reduce the scale, that's all, but the trend will be seen. Right, for sodium, to remove an electron, remember it's the biggest atom, the ionization energy will be the lowest. It's easiest to remove an electron from sodium. Atom is the biggest. Going to magnesium, you'd expect the ionization energy to increase, and it does, atom smaller. Aluminium is smaller still, but look what happens. There's a drop in the ionization energy. We'll explain this in a second. Then silicon, ionization energy is increasing. Phosphorus, ionization energy increases. Sulfur, you'd expect it to increase again, but there's a drop again, the second drop in this period. Again, we'll explain that. Chlorine, ionization energy increases until we get to argon, the last one in the period. Ionization energy is the largest, it's the smallest atom. Okay, so we need to be able to explain this trend. Oh, there's a jump, there's a drop there, and then there's a drop there, and then it carries on. You notice the steps of 2, 3, 3. If you were talking about period 2, there would be a similar drop. Right, there'd be a trend 2, 3, 3 for period 2 as well, and the explanations would be the same. Right, let's see if we can explain the reasons why there's a drop there and there. Right, why is it easier to remove an electron from aluminium compared to magnesium, and why is it easier to remove an electron from sulfur compared to phosphorus? For this, we need to be able to look at the electrons in boxes, the electron arrangements. So in your explanation, draw this. Okay. Right, so if you look at aluminium, its outer electron is in a 3p orbital, and that is quite a high energy level compared to magnesium's outer electrons, which are in 3s2. So because the outer electron for aluminium is in 3p, it's in a higher energy level, then the electron needs less energy to be removed. So I'll just make a note. Electron is in 3p. Is in 3p. It's a higher energy level than the outer electron for magnesium. Therefore, it's easier to be removed. If you look at phosphorus to sulfur, you notice there's 3 electrons in the p orbital for phosphorus. There are 4 electrons in the p orbital for sulfur. And the key word here is there will be repulsion. In the 3p orbital. Now, because of those 2 electrons repelling each other, it's now easier to remove one of those electrons. Repulsion is the cause for the ionization energy drop from phosphorus to sulfur. All right. Right. What we'll do now is have a look at the trend down a group. Okay. We'll pick group 1. Again, in exam they could look at group 2. Let's look at group 1. Lithium, sodium, potassium, rubidium, cesium. As you go down the group, the atoms, you see I've drawn them as getting bigger. Right. Now you might say, well, isn't the nuclear charge increasing? Yes, 3 for lithium, 3 protons. Sodium has got 11 protons. Potassium's got 19 protons. So the nuclear charge is increasing. That should be pulling the electrons closer to the nucleus. But what else is happening here is the shielding effect is changing also. Right? The shielding effect is increasing. Lithium has got 2 shells. Sodium has got 3 shells. Potassium's got 4 shells. 1, 2, 3, 4. So the outer electron is being shielded from the nucleus, the nuclear charge. So the thing to remember here is the shielding effect is way more important than the increase in nuclear charge. So we write down that the shielding effect outweighs the increase in nuclear charge. Now writing that down will give you 2 marks out of 2. Okay, the atoms get bigger, the outer electron gets further and further away from the nucleus, and therefore it's more easily removed. So going down a group, ionization energy decreases, gets easier to remove the outer electron. Atomic radius increases. Okay, right. What we'll do next is we'll have a look at one element and remove all its electrons and see how see what the trend is for that. Let's look at an ionization energy graph for an element. We'll take sodium as an example and we'll take boron as an example. Remember, what we're trying to do is to remove all of the electrons from these atoms. Okay, removing all of the electrons. Let's take sodium first. We know sodium was 281. Alright, there's a nucleus in the middle. It's got 2 electrons there. 8 in the next shell. 1, 2, 3, 4, 5, 6, 7, 8, and 1 in the outer shell. Alright. Now what we are doing is we are removing the outermost electron first. To remove that one, it's going to be the easiest one to remove. So the ionization energy is right down here. Okay. Once you've removed that one electron, that will mean that that shell is no longer available. It's gone. All right. Now you've moved closer to the nucleus to remove the next electron. And therefore, because you move from one shell to the next shell, there will be a massive jump in ionization energy. Like so. Until all these electrons are removed. Right, all in the same shell. There won't be too much of a significant difference in removing all those electrons. So fairly constant, the same main energy level. 1, 2, 3, 4, 5, 6, 7, 8 electrons you've just removed. Right, once they've been removed, that shell has now disappeared. Get all that off. There we are. And you can see now that the remaining electrons are now very, very close to the nucleus. So to remove the last 2, you're going from that shell to that shell, right? Closer to the nucleus still, there will be a massive jump in ionization energy. So there's one jump there, right there, then fairly constant. I'm ignoring S and P orbitals. We could just look at the main shells, main energy levels, and there'll be a massive jump there. Okay. Now, if in the exam they gave you this graph and they asked you to state what group this element was in, this is what you would look at. There, and you notice there's only one electron there before there's a big jump. Therefore, it must have had one electron in the outer shell. It must have been a group 1 element.